Hi, this is Professor Sartor, and I'm back with a few more questions from my college algebra class. This question says, a baseball player swings and hits a pop fly straight up in the air to the catcher. The height of the baseball in meters t seconds after it's hit is given by the quadratic function h of t equals negative 4.9 t squared plus 14.7 t plus 1. How long does it take for the baseball to reach its maximum height, and what is that maximum height? So we have a quadratic function here. We know it's a quadratic function because we have the squared. And we also see that our coefficient is negative. So if we have a quadratic with a negative coefficient, we know that we're going to have a graph of a parabola that's facing down. And then we have some keywords in here that we're looking for the maximum height. And the maximum height is going to occur at the vertex. So we're going to be able to solve this problem by finding the vertex of the quadratic. We're going to use the vertex formula to find the vertex. And the vertex formula has the x-coordinate of the vertex being negative b over 2a. So in our equation, we have that a is equal to negative 4.9 and b is equal to negative 14.7. So that's going to give us negative 14.7 over 2 times negative 4.9. So let's work that out. We got 2 times 4.9, negative 4.9, is negative 9.8. And negative 14.7 divided by 9.8 is a positive 1.5. Then we're going to find the y part of the vertex, which is k, by substituting 1.5 into our function. That's negative 4.9 times 1.5 squared plus 14.7 times 1.5 plus 1. All right, we're going to apply the exponent first. 1.5 squared is 2.25. 14.7 times 1.5 be 22.05. We need to do 4.9 times 2.25. It's a negative 11.025. And 22.05 plus 1 would be 23.05. And 23.05 minus 11.025 would be 12.025. Now, when we have our vertex, it's usually that h is an x value and the k is a y value. However, our function is h of t. Our value of x, our variable that's used in our equation, is a t this time, and that t stands for time. And then our function is named h, and h is what is standing for y, and that is the height. So that's going to tell us what these numbers in our vertex stand for. The h of the vertex, that is standing for time, and so our 1.5 is seconds. and then the 12.025, that is the y value of the vertex, which is standing for the height. So our height was given in meters. So we're going to get a maximum height of 12.025 meters, 1.5 seconds after the ball is hit. Evaluate the expression without use of a calculator. We have the expression log of 100. So first of all, usually we have right here something written down, but there is nothing written there, and so we assume that we have a base of 10. Whenever something is not written there, we have what's called a common log, and the common log has base 10. The way that I'm going to work this out is to pretend like I don't know what the answer to this is, so I'm going to let it be a variable. Then I'm going to rewrite this into an exponential expression or equation because I'm more comfortable with exponents. To rewrite it as an exponent, use the base of the log as the base of the exponent. So this is the base. Then the log always equals the exponent, so that p becomes the exponent. And then this expression 10 to the p is always going to equal whatever is inside the log. So this is going to equal 100. So now I have something that I'm a lot more comfortable with. 10 to a power equals 100. And then I can think, well, 10 to the second power is 100, so that must mean that that p is equal to 2. So now I have log of 100 is equal to 2. And that's what the expression equals. Evaluate the logarithm without use of a calculator. Log base 7 of the fourth root of 7. So I'll rewrite my expression, log base 7 of the fourth root of 7. The strategy is to say, I'm not sure what this equals. Let me rewrite it as an exponential. So I'm not sure what it equals. Let me call it p. I chose p for power because logs always equal the exponent or the power. And then let's rewrite it. So we always start with the base of the log. The base of the log is the base of the exponent. And then the log always equals the exponent, the power. And then 7 to the p is going to equal what's inside the log. So that's the fourth root of 7. So now I've got 7 to the p equals fourth root of 7. So my strategy is to try to match the base on both sides. I have a base of 7 on the left and I have the number 7 on the right. I want to write both sides as 7 to a power. So I can change the fourth root of 7 to be 7 to the 1/4. And now that I have the base being the same on both sides, the exponents have to be equal to each other. So I know that power is 1/4. So I figured out that log base 7 of the fourth root of 7 is 1/4. Sketch the graph of the logarithmic function. Label 3 points that lie on the graph and determine the domain and the equation of the vertical asymptotes. So our function is given to be h of x equals log base 7 of x. We want to draw a picture. We want to find ordered pairs that go with this function. So what I'm going to do is I'm going to switch this to exponential form because it's a lot easier for me to figure out ordered pairs when it's in exponential form. So I'm going to change the h of x to y and then rewrite this log equation as an exponential equation. So the base of the log is the base of the exponent. So it's going to be 7. Then the log always equals the exponent, so that y goes into the exponent. And then this is always going to equal what is inside the log. So x is inside the log. This expression will equal x. So now I've rewritten this equation as 7 to the y equals x. Now I'll come up with a chart. Now when I come up with my chart, I usually choose x values and then figure out the y values with the equation. But because I've rewritten this equation, it's going to be much easier if I choose the y's and figure out the x's. So I'm going to choose my standard set of numbers, -2, -1, 0, 1, and 2, substitute those in to my equation. That's 7 to the first power is 7, 7 to the second power is 49, 7 to the 0 is 1, 7 to the -1. Well, having a negative in the exponent, I do the reciprocal of the base, and 7 to the -2 will be 1 over 49. 7 squared is 49, and we did the reciprocal because of the negative. So let me see what these points look like. So starting with this one right here, we have the ordered pair 49, 2. Okay, that's a little bit too far off my screen, so maybe I should start with this one. That's the ordered pair 7, 1. 7, 1 would be right here. And this ordered pair is 1, 0. 1, 0 would be right here. All right, then I have the ordered pair 1/7, -1. 1/7, -1 would be about right here. So you can kind of see what the picture's looking like now. You can connect these 3 points. The pattern continues on this way, and along this side I have a vertical asymptote. A vertical asymptote is going right on top of the y-axis. It's the vertical line x equals 0. So that's our vertical asymptote. So you can see our picture looks like choice C. The domain we can get from the picture if we use our ruler. If we go from left to right, the graph doesn't start until we get to that y-axis. So it starts at 0 and goes to infinity. So our domain is from 0 to infinity. We don't include 0 because 0 is that vertical asymptote. And then finally, we want to know what the vertical asymptote is. I've already mentioned it is the vertical line x equals 0. Find the domain of the logarithmic function. F of x equals natural log of -4 minus 9x. So what we should know is that logs are only defined for positive values. So you can't take the log of a negative. So log of a negative is undefined, and log of 0 is undefined. The only thing that is defined is log of a positive. So the way we're going to figure out the domain is to take what is inside the log and set that greater than 0. Greater than 0 is positive, so that's what is allowed, that's what's defined. Then we'll solve for x. So we'll add 4 to both sides. That gives me negative 9x is greater than 4. Divide both sides by negative 9. That's x. I need to reverse the inequality symbol because we divide by a negative. And that's a negative 4/9. So to write that in interval notation, I'll first draw a graph. I would mark 4/9 on the graph with an open circle because that point is not included in our set. We have x is less than negative 4/9, so we're going to shade to the left. Then our interval notation, we're going to have a lower bound of a negative infinity and an upper bound of 4/9, parentheses on infinity and parentheses on negative 4/9. So our interval notation would be negative infinity to, I apologize, that's a negative 4/9, negative 4/9. Use the properties of logarithms to expand the logarithmic expression. Whenever possible, evaluate the logarithmic expression. So we're given log of the square root of x over 1,000 y squared. Now the properties that we're being asked about to expand, we have 3 of them, and they are the product rule, the quotient rule, and the power rule. And they match exactly with what we're looking for. The product rule works when you have a product inside the log. The quotient rule works when you have division inside the log. And the power rule is when you have a power inside the log. So when you have a product inside the log, you're going to turn that into the sum of the 2 factors, sum of the log of the first factor and log of the second factor. Whereas when you have division or a quotient, you use subtraction instead. When you have a power inside the log, you bring that power to the front of the log. Basically, you multiply by that power. So that's what we're going to do with the example that we have here. Okay. I have log, and the first thing I'm going to do is change that square root to the 1/2 power. Square root of x and x to the 1/2 power are the same thing. And then I'm going to notice that I've got 3 factors, well, not exactly factors, but 3 separate factors within this expression. I've got x to the 1/2, the 1,000, and the y squared. So using both the product rule and the quotient rule at the same time, I'm going to put individual logs of each one of those factors. So I'm doing log of the x to the 1/2, log of the 1,000, and log of the y squared. Now to be in line with the quotient rule, we've got to make sure that any of the factors that come from the denominator have a negative in front of them. So in front of the log of y squared, I have a minus. In front of the log of 1,000, I have a minus because both of those factors came from the denominator. But the factor that came from the numerator is going to be positive. Then I notice that the first one, log of x to the 1/2, has a power. And the last one, log of y squared, has a power. So I can use the power rule on those. I bring that power to the front, multiplying by that power. So now I have 1/2 log x. And for the last one, I bring that 2 out front. That's minus 2 log of y. Okay. Then the last thing I'm going to do is this one right here in the middle is log of 1,000. That's log of a number. Anytime I have log of a number, I want to try to simplify. Notice it says it in the directions. Whenever possible, evaluate the log expression. So I want to try to work out what log of 1,000 is. Okay, now no base is written. Now when no base is written, we have a common log, and common log is base 10. So I'm not sure what this equals. This is equal to some value of p for power. Then I'll rewrite it as an exponent. That's 10 to the power equals 1,000. 10 to what power is 1,000? That's 10 to the third power is 1,000. So that means that log base 10 of 1,000 is 3. Log of 1,000 is 3. So I can simplify that log of 1,000 to be 3. Use the properties of logarithms to rewrite the expression as a single logarithm. Whenever possible, evaluate the logarithmic expressions. So our example has log base 8 of m minus log base 8 of n. And this time we're trying to write as a single logarithm. Okay, writing as a single logarithm means that we want to be condensing to be an individual log, a single log. So we take a look at our properties here, and I have one with subtraction in it. That's log base b of m minus log base b of n. So when you have subtraction, you can condense that to a single log by using division. So for our example, when we condense, we're going to have a log base 8. Notice both of our logs have log base 8. You can only condense if they have the same log base. And then we're going to condense using division because of the subtraction. The m goes to the numerator because the log is positive, and the n goes to the denominator because that log is negative. So we condense to get log base 8 of m divided by n. Use the properties of logarithms and the logarithmic property of equality to solve the logarithmic equation. The logarithmic equation is this is natural log of 6 plus natural log of x equals natural log of 6 plus natural log of 3x minus 3. So let's talk about this property of equality to know what we're trying to work towards. So the property of equality says this: if you have log base b of m equals log base b of n. So what you have to have on both sides of the equation, you have to have a log with base b, you have to have a log with the same base b. If you have that, what you can say is that what's inside the log on the left has to equal what's inside the log on the right. That's the only way that you could have this equal sign, is if that's true. So you're taking a log equation and simplifying it to something that doesn't have logs. So in order to do that, I have to have a single log on the left and a single log on the right, which I don't have for my example here. I have 2 logs. But we can use the expanding and condensing properties to condense to a single log. So on the left, I have natural log 6 plus natural log x. Because they're both natural log, I can condense them to a single log. And when I condense them, I'm either going to use multiplication or division. And that plus sign tells me to use multiplication. So I'm going to multiply 6 times x. On the other side, I have natural log 6 plus natural log of 3x minus 3. I have natural log on both of them, so I can condense. And when I condense, I'm either going to use multiplication or division. Because of the addition here, I'm going to use multiplication to condense. So that would be 6 times 3x minus 3. So now I have a single log on the left, single log on the right, and they have the same base. They both have base e. So I'm able to use this property of equality that we talked about and say that what's inside the log on the left has to equal what's inside the log on the right. So now I'll solve this linear equation. Let's get rid of parentheses by using the distributive property. That's 18x minus 18. I'll move all the x's to the same side. I'm subtracting 18 on both sides. That gives me a negative 12x equals a negative 18. I'll divide both sides by negative 12. And that'll give me x equals, and let's reduce that. 6 goes into both of them. That will be 3 over 2. Now with every log equation, you need to check. And what you're checking for is to make sure that you never take the log of a negative. So in the original, I had natural log of 6 plus natural log. Let's substitute that 3 over 2 equals natural log 6 plus natural log of 3 times 3 over 2 minus 3. Let me write that a little clearer. That's natural log of 3 times 3 over 2 minus 3. So this is log of a positive, this is log of a positive, this is log of a positive. Let's just double check. 3 times 3 over 2 would be 9 over 2 minus 3. 9 over 2 is about 4.5 minus 3. So that is a positive number. So our solution checks out and we'll keep it. Use the properties of logarithms and the logarithmic property of equality to solve the logarithmic equation. 2 log of x plus 5 equals log 18 plus log of 2. So let's make sure we know about this property of equality so we know what we're working towards. The property of equality says that if you have log base b of m equals log base b of n, then m equals n. So basically, if we can get the log with the same base on both sides, then we can simplify our equation to be something without logarithms in it. So let's try that with our example. We have 2 log of x plus 5 equals log of 18 plus log of 2. So in order to use this property of equality, I need to have a single log on the left and a single log on the right. This 2 that's in front of the log is preventing me from having a single log. So I'm going to use the power rule, and the power rule moves that 2 to the power of the log. So we have log of x plus 5 squared. On the right-hand side, you can see that I have 2 logs instead of a single log. So I'm going to condense. I'm allowed to condense because they have the same base. And when I condense, I'm going to either use multiplication or division, and I'm going to use multiplication because of that plus sign. So I'll use 18 times 2. So now you see I've got a single log on the left, that's base 10, a single log on the right, that's base 10. So I can use the property of equality to say what's inside this log is equal to what's inside this log, which is 18 times 2. How much is 18 times 2? 36. All right, so now I can finish solving. The logs are gone, and this is a quadratic equation. I'll take the square root of both sides. The square root and the square cancel each other out, and I pick up a plus or minus sign on the other side. I get square root of 36 to be 6, and I'll subtract 5 on both sides, and that's x equals negative 5 plus or minus 6. Negative 5 plus 6 would be 1, and negative 5 minus 6 would be negative 11. And we need to check. So let's check. Our original is 2 log of x plus 5 equals log of 18 plus log of 2. So I'm checking the x equals 1. If I were to plug a 1 in for my variable, would I have a positive in here? And I would, so I can keep that. If I plug in a negative 11 in for my variable, that gives me a negative inside the log. You can't take the log of a negative, so I'm going to throw that solution away. And the only solution would be negative 11. Use the change of base formula and a calculator to approximate the following logarithmic expression. Log base 1/5 of 73. So let's talk about what the change of base formula is. Change of base formula allows you to take any logarithmic expression and change the base to something else. Right now we have a base of b, but we may need to have a different base. Some calculators only allow you to type in base e or base 10. So that's why it's usually used hand in hand with the calculator. So if I wanted to change to a different base, this is how I would write it. Log base a. That base a is the base that I'm choosing to change to. And you're going to use the value inside the logarithm, in the log on the numerator, and the base of the logarithm as what goes inside the log in the denominator. So for this example, I have log base 1/5 of 73. And on my calculator, I have two buttons. I have the log button, and I think there's log button. And I have the ln button, that's natural log. So I'm going to choose to go to one of them. Log is base 10, ln is base e. So if I went to base 10, it would look like this. Log of 73 over log of 1/5. If I use natural log, it would be natural log of 73 over natural log of 1/5. So let's try both of them. Log of 73 divided by log of 1/5. And I get approximately, it says round to 4 decimal places, negative 2.6658. And if I did natural log 73 divided by natural log 1/5, and you see I get the exact same answer, approximately negative 2.6658. So this question says, solve the exponential equation e to the x equals 4. So I wrote over here some of the different methods that we can use to solve exponential equations. The first one is relating the bases. So you try to make the bases the same on both sides. We can't do that in this example because one side has base e and the other side doesn't have the e. So then we have these other two options, which are to convert the exponential equation to a logarithmic and also to take the log of both sides. Either one of those methods will work for this example. So let's try both. So if you have e to the x equals 4, and you try to take this exponential equation and write it as a log, you would write the word log, and then you're going to write the base of the exponent is the base of the log. So that's going to become base e. The log always equals the exponent. So this exponent here is what that log equals. And then this 4 that's on the other side of the equation is what goes inside the log. So we end up with log base e of 4 equals x. Now we don't typically write log base e. We have special symbols which are the natural log. So we use natural log when it's log base e. And we have our equation solved. We have x equals natural log 4. So that was with this method of converting it to a logarithmic equation. Okay, let's try it again using the other method of taking the log of both sides. Okay, so if we have e to the x equals 4, we're going to take the log of both sides. You can actually use any log you want, log base, but I always use natural log because it's available on your calculators. So I'm going to do natural log on the left and natural log on the right. Then I'm going to use the power rule to bring this power rule, the power rule for logarithms. So it brings the x out front of the log. And then if we were to try to simplify natural log e is equal to something. Now earlier I told you that the base of natural log is e, so that base to the power equals what's inside the log, and we get e to a power equals e. So that means that power has to equal 1. Natural log e equals 1. So I found that natural log e is 1. That's x times 1 is natural log 4. X times 1 is x. So you can see that we got the same answer, x equals natural log 4, using either way.